let's go ahead and write our add method so we can now populate this. So again, we're going to write a wrapper method so we can easily add items without having to worry about our starting point. So public void add e item. So and here what this will do is it will simply do and this will look a little weird actually. This dot head, and the reason I'm going to, or this dot root is equal to the result of adding this dot head item. Root. All right. I'll explain this in a second. Private node e add. So here we're returning a node. It's going to take in a node, which is going to be the root, and it's going to have an item. So return null right now to quash it. So here we're saying whatever the result of add is, we're going to add the item to the root. Okay. We're going to add this item to the root. We're going to put it in its proper place, and we're going to set up the root to be this. Now, the root might not actually change. In a lot of cases, it won't. So this will simply be like returning the same item, but we'll see that. Now, the reason I'm doing it like this is to make it symmetrical with the delete when we get to it. It'll make more sense when we get to delete. Okay. So we will go ahead and take a look at doing this. So, and this is about as far as I can get without having to draw. Okay. Hopefully I could do contains without having to draw, but at add, I feel like drawing is not a bad idea. So, here, base case again, if root is equal to null. Now, not the root of the whole tree, but just simply the root of this tree, of the subtree is equal to null, then we found a place to put our node. So we are going to return new node e item. Or not e item, return node item. So that is what we're going to do here. All right, as I previously mentioned, it's a bit hard going on with add without actually having a drawing, so I've went ahead and made ourselves a binary search tree over here. So these nodes over here, by the way, are just simply the nodes that are just spare nodes for me to use. But let's go ahead and just take a look at basically ignore this for a second and suppose this is our tree, nothing, right? If the root is equal to null, then what do? We create a new node and we make it the root of the tree. Suppose we were adding 6 to this binary search tree. And we would just simply say, oh, we'll take 6, make it the root, and now we return it over here to this dot root. Right? But let's go ahead and see what we're doing. So we're going to do the same thing over here, which is that if, so we're going to do int comparison equals item dot compare to root dot item. So first thing we have to do is figure out what we're going to do about duplicates. And I'm going to just make a rule right now for that I haven't made in previous semesters, but it's going to make it easier for me. Ooh, looks like I'm like wearing a tiny crown. That's cool. So the rule I'm going to do for duplicates is if there is a duplicate, then we just do nothing. So if so if we're trying to add an item that's already there, so if comparison equals 0, we're going to return we need to return a node, so we're going to just return root. Now, why did we return root? Because essentially when we return in the add and remove methods, we're using this return statement as a way to communicate what to change my child to. And we're saying, don't change me, parent. Don't change me. So otherwise, let's take a look at what we've got over here. If comparison is equal to -1, or sorry, is less, sorry, not, so if it's less than 0, right, my fingers and hands were saying different things, then that means that basically that, right, so suppose we want to add 6 to this tree over here. Then what we need to do is that we need to check, okay, we want to add 6 to this tree. Where do I need to add it? Well, it's not a duplicate of what's here, so we want to go to the left. Comparison is less than 0, then we want to add it to here, which means add it to this subtree, right? 6 is less than 15, so it should go on the left side. So add it to this subtree. So what we'll do is we'll say, hey, this dot, or rather, root dot left is equal to, so root dot left is equal to this dot add, sorry, root dot left is equal to add root dot left item, and then return root again. Almost wrote return toot. And then you can probably guess what goes over here. Else root dot right is equal to the result of adding root dot right, or adding the item to the right tree, turn root. And now we can remove that, return null, because it's unreachable. So when we add 6, let's go ahead and see what happens when we add 6 done, because this is better explained by example, why this works and how this is working. So 6 and 15, we go over here, we say, okay, we compare 6, we compare 6 to 15, 6 is less than 15, so we go to 10. So we call root.add to the left tree. Then we compare 6 and 10, we say go to the left. Then we say 6 and 7, and again we say go to the left. Now over here, we're adding it over here. Root in this case is null, so I'm going to return, so I'm going to create a new node and return it in one line. Okay, so I'm going to make this new node and return it. And now where am I returning it to? I'm returning this, the memory location of this new node I created over here. And so we're in this line now for 7, where root is 7. So this gets set to 7's dot left as a result. So that line takes care of that. And now we return root. Now 7 gets set as 10's left subtree, which it already is. And then 10 gets set as 15's subtree, which it already is. Right? That's what the return root is doing. We're just simply telling our parents, hey, we're not changing. Why am I bothering doing that? And the answer is because it makes it easier to program, even though it's weird to look at. It's symmetrical with the remove method we're going to do. But also, just as importantly, if you decide to take a look at the way the self-balancing binary trees look, sometimes that what you return to your parent will change. Sometimes your child will change, so that's what this is for. To be in the same kind of format as that. Right? And let's take a look at adding 12 to this tree. Okay, so 12 less than 15, greater than 10, less than 13. So we'd get over here, we'd create a new item, and we'd say, hey, this should go on. So this gets returned over to here, where root in this case is the node that contains 13. So again, we attach it to the left subtree. And then 13 returns itself to 10, becoming 10's right subtree, which it already is, and then 10 becomes 15's left subtree, which it already is, and then 15 returns itself to the add function, which sets 15 to be the root, which it already is. But now I don't have to have a special exception for basically adding the very first item. So let's go ahead and write a function that's going to test this for us.